Hello everyone, my name is Emily J. Hewitt, and this is my Lab 4 presentation on Faraday's Law. The main purpose of this lab was to examine and apply Faraday's Law and its effect on a bar magnet. We obtained real-life data and compared that data to a computational model. The results of my experiment were that the experimental time average was 1.592 seconds, the computational time was 1.394 seconds, with a difference of them being 0.198 seconds. So models and principles. The model was a bar magnet falling through aluminum foil, the system being the magnet and the foil, where the surroundings were everything else. The fundamental principles included the Biot-Savart law, which we used this to calculate the magnetic field produced by the moving magnet, and later the magnetic field associated with the induced currents in aluminum rings. We used Faraday's law to show that as the magnet falls, the magnetic flux through each aluminum ring changes, changing the flux that induces an EMF, which drives the current in the foil, and lastly Newton's second law, which after calculating all the forces on the magnet, we used Newton's second law to determine the magnet's acceleration, velocity, and position over time. We began with the initial conditions listed below, those of the aluminum foil listed, and then as well as the magnet's mass, it being 0.028 kilograms. For the experimental model, we dropped the magnet through a tube and calculated when it first entered the tube to when it left the tube. We did this over 5 attempts with the math included here and ended up with an average of 1.592 seconds. We then moved on to a computational model where we used step 2 to create a function to calculate the magnetic field of the bar magnet, step 3 where we edited to create a function to calculate the magnetic flux, step 5 and 6 we edited to compute the typical B field at each ring, and step 7 where we used the F net to calculate the net force on the magnet. And then as you can see, this is the results of our computation model with the time in the tube in seconds listed on the very bottom right at 1.394 seconds. We then moved on to interpreting the simulation. We figured out which color corresponded with the clockwise and counterclockwise current using Lenz's law. We determined that the blue indicates clockwise and red indicates counterclockwise. We then noticed what happens to the dynamics of the system when we flip the magnet around. The results would be the same, however, internally the current and the magnetic poles would be flipped. We then answered how does the total time in the tube of your real-world simulation compare to that of our computational system? How might the computational system be made more accurate? We said the computational model could be improved by increasing the ring amount to use to emulate the tube, and that we could also account for the drag and inconsistencies of the dimensions of the foil tube. We then answered what does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? We said that the forces started out as a very imbalanced but eventually evened out. For assumptions, we assumed that the measurements were taken correctly and that Lab 3 was done with precision. For errors, we noticed that there could be human errors in scrubbing the video to obtain the values and also coding errors. Overall, though, the computation versus calculation models matched fairly solidly. What if? So what if the resistivity of the conductor were reduced as close to possible as 0? As the resistivity decreases, the current would increase. This means the magnet would take significantly longer to fall through the tube as the braking force in Faraday's law would increase. What if the holes or slots were cut into the tube? How would this affect the ring currents in our model? Holes would majorly mess up the current flow. The braking force of the magnetic force would decrease, which would ultimately cause the bar magnet to fall faster. Thank you for listening.